Up to this point, our series convergence tests have only applied if the terms of the series are fairly simple and the series meet certain specific criteria, like, for example, being a p-series or a geometric series, or the couple of things that you have to verify when you do the integral test. So a slight difference between two series can make a test no longer applicable. So for example, 1 divided by 2 to the nth power is geometric because you could write that as 1/2 to the nth power. But if you have an n on top, that is no longer a geometric series, so you can't use the geometric series test. Similarly, 1 over n cubed is a p-series, but 1 over n cubed plus 1 is not a p-series. This one right here, n over n squared plus 3 squared, is easily integrated, but this one is not. It's more challenging to integrate something like that. So in this section, we're going to study 2 additional tests which allow us to compare a series with a more simple series that we can test for convergence or divergence. The first of these tests is called the direct comparison test. If we have a sub n between 0 and b sub n for all n, if the series b sub n the sum of b sub n converges, then the sum of a sub n is also going to converge. If the sum of a sub n diverges, then the sum of b sub n is going to also diverge. So the order of this matters. If you have a larger series converging, then the smaller series is also going to converge. But if you have a smaller series diverging, then the larger series is also going to diverge. So basically, if you've got a larger series that is approaching some value and it's going to converge on it, then you know that this one also has to converge. If you've got a smaller series, like say just if these were the dots along the point, and you know that it's diverging, it's growing, it's not adding up to a simple value, then any larger series will also have to diverge. So one thing that's important to understand about these tests is that they don't actually tell you what they converge to. If they converge, it doesn't tell you that value. It just says yes, it converges, or no, it doesn't. And it only gives us certain scenarios. So it only says exactly what it says. There are some combinations that don't work. So these are all don't try this test if you have these scenarios. You can't use the test if b sub n diverges. This is not going to give you a sub n diverging. So the smaller, if a larger series diverges, that doesn't necessarily mean that the smaller one has to. If the smaller one converges, you can't say that b sub n must also converge. That's a no. And the larger series diverging, you can't use this to say that the smaller series converges. And if the smaller series converges, you can't use this to say that the larger series diverges. It only says exactly what it says. You can't use it for these scenarios, only for this one. So this first example says use the direct comparison test to determine the convergence or divergence of the sum from 1 to infinity of 1 over n squared plus 1. This looks to me like a p-series, and we need a larger series that we know converges to compare this to. So I'm going to observe that for all n, we can say for sure that n squared is less than n squared plus 1. If you add 1 to something, you get a larger number. So if I want to compare this, if I want to say get a 1 on top of this, I might divide by n squared times n squared plus 1 on both sides. And if you do that, you'll notice that, n squared plus 1, those are both positive, so we don't have to change the sign of this. But this gives me that 1 over n squared plus 1 is less than 1 over n squared for all n. So if we let this sequence be our a sub n, and we let this sequence be our b sub n, then we have a sub n is greater than 0 and is less than b sub n. So what we're going to do then is we're going to consider the sum from 1 to infinity of b sub n to be the sum from n equals 1 to infinity of 1 over n squared. And this is a p series where p equals 2, which is greater than 1, so this converges by the p series test. And since our a sub n is less than b sub n for all n, we can say that the sum from 1 to infinity of a sub n, which is going to be the sum from 1 to infinity of 1 over n squared plus 1, also converges by the direct comparison test, which I'll shorthand to be DCT. So all of these pieces are part of this. We're showing, first of all, that we get this relationship. Then we're showing that b sub n is something that converges. And then finally, we're applying the test to show that our a sub n also has to converge. Let's look at this one. I want to use the direct comparison test to determine the convergence or divergence of the sum from 1 to infinity of 1 over 2 plus 3 to the nth power. So a much simpler version of this would be 3 to the nth power. And I can observe that 3 to the nth power is greater than 0. It's never going to be negative. And it's less than 2 plus 3 to the nth power. So in a similar fashion as what we did before, 1 over 2 plus 3 to the nth power is going to be less than 1 over 3 to the nth power. And of course, both of these things are positive, so we don't have to worry about that. So we'll have 0 between a sub n between 0 and b sub n, and we'll call this one right here our b sub n. So the sum from 1 to infinity of b sub n will be the sum from 1 to infinity of 1 over 3 to the nth power, which we can write as the sum from 1 to infinity of 1/3 to the nth power, because you could have 1 to the n over 3 to the n. So this would be r equals 1/3. The absolute value of that is less than 1. So this is a geometric series with r equals 1/3, and it converges. So therefore, by the direct comparison test, the sum from 1 to infinity of 1 over 2 plus 3 to the n also converges. So we've got a larger series that converges, so therefore our smaller one must also converge. Here we have 1 over 3n squared plus 2. So the most simple version of this would just be the n squared, and I know that n squared is less than 3n squared plus 2 for whatever value of n you have. So because this one would make a larger denominator, that means 1 over 3n squared plus 2 is less than 1 over n squared. And of course, both of those things are positive because you're squaring a number and adding a positive number to it. So this is going to be our a sub n, and this is going to be our b sub n. So we have a larger series, 1 over n squared. This is a p series, which converges because p is equal to 2, which is greater than 1. So by the direct comparison test, the sum from 0 to infinity of 1 over 3n squared plus 2 also converges. Now with this example, I've got 1 over n minus 2, and I'm going to observe that a more simple version of this would be 1 over n. Now normally we've been looking for a larger series, but in this case 1 over n is actually going to be a smaller series because n minus 2 is less than n, okay? And for n greater than 2, that is positive. So I'm going to be looking at n greater than 2. The first two terms don't really matter because you can calculate those. We just want to know what happens to this thing long term. So I have that 1 over n is less than 1 over n minus 2. And again, if n is greater than 2, both of those things are positive, because we would have a smaller denominator here, which makes for a larger fraction. So my series from n equals 0 to infinity of a sub n is going to be the series from 0 to infinity of 1 over n. And this is the harmonic series that we talked about in the previous section. And this diverges by the p-series test. P is equal to 1. So with this one, this would be my A sub n, this would be my B sub n. And since I have a smaller series diverging, then the sum of the larger series, which is 1 over n minus 2, also diverges. And that's going to be by the direct comparison test. So you can see both versions of it. We have to verify this part. We have to verify that the smaller series diverges, and then we can make our conclusion.